Okay, we're on. Hopefully, I don't run out of space or some stupid ass thing. All right, so bad news, not working. But shall I start with the status of where it's at? I mean,
Yeah, but you were quite confident that would work, but fair
I
enough. Live
didn't,
demos.
I didn't
Uh,
have want to project that, but the place I'm at is like this should work, but whoops, it didn't. Why not? Which is different to like, I know it doesn't work because I haven't finished it yet. This is
yeah,
like
yeah,
I think I finished, and now I'm finding reasons why I haven't finished.
yeah, yeah,
Um,
yeah, yeah.
so part of what the recent delays have been is that I have the amount of time it was taking to make a change and then deploy it was getting too large, and the number of places, different places I had to look to find errors was frustratingly large. So errors could have been split across um, one, two, three, four, maybe five different cloud computers, which is very annoying to do. So what I figured out how to do is I made a mock that can run everything, but
Okay.
in the local computer, so it can just it was actually this thing here called the orchestration test,
Mm-hmm.
which can boot up a local instance of everything so that it's easier to
Mm-hmm.
get the bots to go through what the problems are, because the key to AI programming, particularly when you're dealing with infrastructure, appears to be able to say to the bot, look, here's the code, here's how you run up the mock, or here's how you access the infrastructure. There's errors in the logs, fix it. And then it
Mm-hmm.
sort of loops around, and it like does web requests using curl, looks at the logs, starts processes, and it does a really good job of getting there. But until oftentimes it's hard to be able to arrange the system to the point where the bot can be pointed at it like that without it going wildly off into the distance trying to fix everything or shit that I don't want fixed or didn't mean to be fixed. And then you end up with like slop, which is a new kind of problem because now I have to digest the slop and be like, oh, that, it starts to burn time, where that's kind of the key, like not getting drowned in slop.
So how did you constrain it though?
Um, First of all, multiple runs and then throwing out what it did and then running again with the knowledge of the previous runs flop.
Okay.
So, like, starting out, detecting what I don't like, and then going, oh, okay, start again, bang. Um, the second thing is making well constrained units underneath. So I spent time to manually make sure that the this thing, for example, uh, could be not that one exactly. This thing was like, this is how I want the mock to be started, and
Okay.
so
So
like
you handcrafted that.
well, yeah, but I handcrafted it down because when the bot made it, it made it to be easily 5 times the size of this file. And I was
Mm-hmm.
like, no, mate, you don't need all that, all that, all that. And so I like hand pruned it and then was
Right.
like, using this as the example, do this other thing. And then
Right.
even when it did the orchestration test first, it came out with, there used to be like 5 different files here, and they were massive files, and it had done like all sorts of shit. And I was like, no, no. And
Mm-hmm.
part of it has been um, using a technique called dependency injection. If you don't, which is to say, like, some things when you need to run them, like the exec application the exec application needs to interact with the fly infrastructure.
Yeah.
And so dependency injection is a programming technique where I supply a function that has a fairly simple signature. Like this basically just says, where's a good example? Here's an example of start instance, right? This is the function that starts a new host by creating a fly machine and then booting it. And so the function parameters are real simple. It's like, hey, here's the state that I want, and here is the computer ID I want you to do it to. The actual implementation is all this stuff, which is the minimum that I think you need to talk to Fly about. But dependency injection says that I take this function and I provide it when I call the hardware reconciler, which means that I can mock that function and I can make it work in this local environment where spinning up a new machine is not contacting Fly. It's just simply starting a new child process and setting some ports and stuff. And so I rewired the app to take these dependencies so that they could be injected at mock time, but also work in Fly. And then that's how I sort of hand-picked through that to make sure that the function signatures were clean, which seems to be a good, strong AI programming technique, is if you get your function signatures really tight and insist on them, and then let the bot work with those signatures, you get a better result.
That makes sense. Yeah.
Because you're basically controlling the API between the components that you want, and then letting the bot go in there and fix up on the inside. I also made this other little tool, which was if I go to supervisor and I start up the dev server that I made today, this will give me basically a browser of the that tests the supervisor that controls each host, so that I can run it in a mock and make sure that it works. But I made an extra tool for that, which was called DenoTask MCP. And what the MCP, this is the little app I made, which probably looks a lot cooler than the amount of time it took me to get the bot to do it, which is what I love about AI coding, right? Is that if you really get it right with the constraints, then you can just be like, do this thing, and it's like so what this does is it lets me say, so I can specify the host and the port, but because these are all running on defaults, I'm just going to roll. I don't need to specify that. I go DenoTask MCP start. This is going to start an interaction, and then I say serve, because that's the special keyword I added. Serve cookie time. Okay, and now I got back an interaction ID, and so I go DenoTask MCP status of interaction ID 1, which says that it is pending. Is that right? Maybe that is right. Then I go DenoTask MCP I think I want to go. Oh, what happened there? Oh, that's right. Sorry, I wasn't. I should have been watching this. so when I go, so that's interaction ID 1. It created this thing, right? I can go to that, and now that is saying, what's it saying? Serve dev default view. That wasn't what I wanted. I wanted something's not right here. Anyway, point is, this is a way to, this is what this is doing under the hood, is it's doing MCP calls into that server.
Okay.
So where that's really supposed to get cool, right, is that I go into Codex and I say, use the Deno Task MCP tool to exercise the dev server that is already running on. Fuck, where was it? This is what I should have gone to. Sorry, my bad. That's serve cookie time.
Uh-huh.
So that started up a new service on a new port and yada yada yada. But that's not the cool bit. The cool bit is if I get to where the fuck this thing started, it was like, okay, we are running on. Am I stupid? Like, where is the? It should tell me. Oh, here. Sorry, my bad. Right there. So if I, that wasn't what I wanted to do. That was the wrong button. Go here. I copy the thing. Already running on this address. I say go. I come down here. I wait patiently. I said I wait patiently. Okay, here we go. Now it starts calling different functions on the supervisor, which is the thing that controls the agent.
Oh, scroll up. What happened there?
Up here.
Hello world, hello world. Yeah, completed. Are up the highlighting. Data showing. Okay, all right.
Right, and you can see that it's in here. There's like interaction status. We should be able to see calls where it came in. See input hello world.
Yeah.
Yeah, so that's an example of the bot being able to call the agent in a test environment where it's acting as though it was a remote agent and it's doing it to exercise the system. And now I say, now exercise the web serve functionality and test that the proxying works. So now what it's going to do is it's going to use the agent-to-agent communication framework, again, still begging for a name there, where it's going to tell the agent to start up a web server, and then it's going to get that web server to proxy a call through as though it was running as the fly service, so that you hit that public URL with the SSL cert and then got proxied through to the local port so that you can run up any service you like on the agent itself and then see it in the browser.
Right.
Does that make sense, or does that sound overcomplicated?
No, we're getting close to my RAM on that one. Say that again.
When you contact an agent, like here, right? So this is the name of my computer, obviously not chosen cosmetically, and this is the name of the agent on that computer that I'm talking to.
Yep.
When I come in on this address, it's actually hitting port 443, which is the SSL cert, right? Because connection is secure, which means that we're on the default port.
Yeah.
If I also wanted to start anything that was running on a different port, now I don't know if this port is actually working, it might be. But if I want to run something, oh no, it's not. So if I want to run something on a different port and then access it from this public URL,
Yeah.
what it does is it takes in this request with all the the auth, the SSL, all that stuff, and then it proxies it or points it to the local port on the agent box, so that me as the remote browser, any service that starts up on these agents and exposes a port can be viewed in my browser.
Okay.
Which is very powerful because you can get things like file browsers, web pages, dev servers, video calls, anything at all, and it's all accessible through this model.
Right.
So for example, you'll be in there in a codex session and you're like, hey, okay, fire up the dev server, I want to take a look at this, and it's like, all right, it's on port 5555, and then without this feature, that's where your journey stops. But here you just go, it would just create you a link, you would browse to it, now you're looking at the
That's pretty cool.
thing, and it can be anything.
That's pretty cool.
So I don't know if that was, it sort of felt like, yes, we needed that feature long term, but it also felt like without that feature, immediately things get pretty choked, I guess. Like if you can only talk to one web server port, you're not really able to do genuine development or work, because you can't, all you can do is talk to the agent. You can't ever see what it did or the products of it. Can't ever serve more than just the agent.
Yeah. Yeah.
And that seemed critical, because otherwise, what are you going to do? Start up a whole nother host and then remotely control it to just be that thing? Well, now you're not able to run a hot reloading dev server as the agent makes changes. Like without that multiple port thing, you lose what felt like 90% of the functions.
Yeah.
So
Yeah.
it did complicate things.
Doesn't scale well either. The previous one.
No, so it did complicate things, but maybe that's okay. But yeah, I mean, this is just how I've been testing the system, because whilst it sounds complicated, I'm convinced that it isn't, because I keep finding ways to compact it down. So this file is probably the heart of the whole app, and it's not that big. Like I could cut it down more, but sorry, not that one, although that's quite important. This one is really the heart of it all. This is the app that we were just interacting with. Like this seems to be the app that you always interact with, because this is the face of the agent. Like this is the controller, the supervisor of the agent, and it's what handles everything, like receiving agent to agent communications, presenting all of the MCP servers that the agent.toml specified back into the agent, doing that routing, the proxying that I tried to show you there, where it sort of goes to another port. All that stuff is done by this folder and these files.
Okay.
So
That's quite a lot of information. I don't have much to go back with other than, yeah.
I've got like the codex. So I didn't have to rewrite the way that the agents are packaged, but when I stripped out the faces concept, it struck me that there was a much cleaner way to package what an agent is, because I know that the first thing that you're going to want to do, the first thing that I'm going to want to do is to vibe code more agents.
Yes.
And if the way that I'd set it up before, an agent was very tangled up with the host and the supervisor and all that. So the effort over the past week has been to cleanly separate out what an agent is so that it can be treated as a module that gets loaded up. And that also means separating out what a host is to be, a host used to have actual supporting JavaScript around it before, but now a host is just the Docker file. So it's just the tooling that comes in the operating system, what the operating system is, what the base user is, what Linux packages are installed. Okay. Obviously, for the coder image, it's a lot more. A few environment settings that are required for the particular use case, and that's all that a host is. And then what you see here, this thing, is running the supervisor. So that's this bit.
Right.
It all runs that one thing, and that's the heart of it, the supervisor.
Right. Okay. Now, that's quite good. That's quite interesting.
Now, the supervisor does some special things. First of all, it boots and it sits there, and it waits for. It runs a special MCP server that's the admin level MCP server that takes one and only one command, which is load this agent. And so it boots and it waits and it says, okay, I'm a host and I'm waiting. And in Cocoa World, what that would mean is I've booted, I've passed my attestation checks, I'm now ready to receive private information and do private workloads. So it comes up, sits there, joins the queue, it's ready. Then when the manager of the execution says, okay, load this agent, what it's really saying is, here's a computer ID, here's the path to the agent folder within the file system, load up the agent that specifies. And so that triggers the process to, at the moment it doesn't really read the agent toml, so I shortcutted that, but the purpose there is it will read agent toml, it'll read up previous history, it'll read up whatever the particular agent that was told to run there needs or has set up. It'll boot its Git repos and all that, and then once it's ready, the supervisor goes into this seemingly complicated mode, but I hope if you let me explain it, it seems pretty minimal for the features we want, because there's some, like, we want an agent to be able to call other agents, be called by other agents. We want the agent to have tooling that was presented by the agent.toml, and we want it to be able to receive web requests to arbitrary ports on the inside, right?
Yeah.
That seems to be the complete feature set. So what it does, once it's loaded the agent, keeping in mind, like, there's also the need for security and process isolation and all that. Now that we've got this additional requirement where we realize that part of the host has to remain privileged, and then run the supervisor in this privileged zone, and then run the agent in a deprivileged zone.
Yes.
Right? Yeah. So what it does then is it runs the agent as a standard IO MCP server, which was the sort of the original type of MCP server that got popularized and what everyone's kind of used to.
Mm-hmm.
But what that means is that agents get packaged as standard IO MCP servers. And so all you got to do to make an agent is you got to present me with something somehow that I can call from the Linux command shell, and when I run that command, I'll get back a standard IO MCP server that responds to that interaction protocol.
Right. And
it can do other things, but it must at least provide those tools.
Yeah. And at that point, you've got agent to agent because you can't escalate your privileges, and also there's no crosstalk.
Yeah, because it's an isolated process. There's no getting around that. Like, it's in a box. This is the thing.
Yeah.
But then the supervisor does this other trick, which is when it boots, it passes in. It's in complete control of the environment variables that it passes into the agent that's about to boot. One of those environment variables is an API key that lets that agent, if it wants to, make web-based MCP calls to the supervisor itself, which is how I present back the tools from the agent TOML.
So does everything go through the supervisor then?
Yes, everything goes through the supervisor.
Right.
That's why that process has been...
That's pretty neat, actually. Yeah, okay.
Yeah, because it makes the supervisor quite delicate to get right, but it also means that when it is right, everything's right, because there's not like this separate process and this other thing and this. Now I got port contention because so the supervisor runs on one port and it's one process, and it starts child processes that represent the agent standard IO MCP server, but also a child process that represents the agent.toml MCP tools that are going to be accessed by that agent. So it allows me to keep separated the agent code and the agent TOML tooling code, because those two things might be enemies of each other, but they're all definitely enemies of us. So
yeah. No, that's quite sweet.
So that's why that was a little bit gnarly.
I have to admit I'm not following all the details on this one because it does feel gnarly. But the your last point makes eminent sense.
So may I try and draw a picture? Because I feel like for my own sanity, I need to be able to justify it. Set the canvas. Okie dokie. Here we go. My terrible hand drawing thing. Crayons aplenty. I'll grab a red crayon. So the supervisor boots. It gets told to load an agent. It then goes and starts a standard IO process, which makes the agent.
Yep.
So long as you tell me how to start your process, it could be Python, it could be anything. So long as you tell me how to start it on a Linux box, I can run your agent.
Right.
Then, based on the agent.toml, in a separate process, we also start the MCP tools, which I'll just denote M. I'm not even going to try and write the C and the P. It starts the MCP tools that go with the agent.toml that specified this agent in the first place. so that
Yeah.
when this agent wants to make a call to its own MCP server, MCP tooling that it expects to be there, it makes a web-based call into the supervisor, which then comes down and is processed by this tooling, which is standard I/O tooling, but it was routed through the supervisor.
Is that for every time an agent who knows about an MCP that it has access to
Yeah.
goes through the supervisor,
Correct.
which keeps it nice and clean?
Well,
Okay.
because I gotta keep these guys need to be kept apart because they're enemies, but also they're enemies of us. So we
Right.
gotta, right?
Right.
Like, because this is arbitrary code that's separate from this arbitrary code,
That's
and
a
we are
gas mother. Yeah.
not arbitrary code.
Yeah.
And then additionally, the agent also has MCP tooling that presents in the same way as this MCP tooling, but that MCP tooling is the agent, the communication with the, I mean, give me a name here. It's the hypercomputer thing, and
Yeah.
that is what then goes off to make calls to other agents, starts
right.
agents.
Okay. Penny drops. Right. So the agent just needs to know is only talking to one thing here.
One MCP server, yeah.
Yeah. And it gets access to an arbitrary number of MCPs.
Yeah.
And the hyper,
Yeah,
the
that one
hyper-
MCP server
hypervisor.
presents as all of these MCP servers that are loaded in isolation, but also it gets access to the MCP tools that give you access to the rest of the hypercomputer.
Oh, that's
And this stays completely isolated because it's
Yeah.
standard I/O only. There's only like standard in, standard out, standard error, and that's it. The supervisor process is in complete control of that process. So there's no like, whoopsie, I left a port open. Whoopsie, I need some auth for this agent. All you got to do is make a standard I/O MCP server, and we can run you as an agent provided you meet the minimum tool listings.
right. And in this diagram, how does one agent ask another agent to run an MCP that it has access to, but the original agent doesn't?
It calls, first of all, it either starts the agent or finds the agent using the hypercomputer MCP tools. And then once it's found a suitable candidate, it uses the interaction start, which is that plain text string that says, hey, fellow agent, can you please run this MCP tool that you said you had access to, and then give me the result. And then it whirs away, and it comes back with the result as a plain text string, and now and maybe some files, and now this agent can access it.
Does it go through the supervisor for the result?
Yes, absolutely. Everything goes through the supervisor.
Okay, all right. That is very parsimonious and really quite elegant.
Yeah, it's a nice thing to say. Bit of a head scratch. Oh, and the last thing is like when external web traffic comes in, the supervisor proxies it into I'm sorry, that's not how it goes. The line has gone astray. So if the agent decided to start another process that was like a dev server or something, I'll just call that D for dev, which I might add is now the enemy of everyone.
Yeah.
But we want to access it over the public internet, provided you have authenticated with this particular agent to be allowed to access that
Yeah.
port. your request in orange comes in to the supervisor. The supervisor looks at it for shit like, is this guy even fucking supposed to be here? And then, if it is, and the port you asked for, it proxies that through to hit this thing. And now you are talking to this thing as though you were talking to the supervisor, as though the supervisor was the dev server.
Right. Right. Right.
So
So as an agent, all I have to worry about is I just ask the supervisor for anything I want,
Yep.
MCP,
Yep.
service, whatever service.
You can start any process you want and bind to any unprivileged port that you want.
Yeah.
And then you can advertise or tell your users about it or anyone else about it. And then they can browse to it. Provided they can access the agent and they've got permissions for that port, they can browse to it.
Right.
So I know that diagram looks a bit like the London Underground, but...
No, it doesn't. It actually makes... now I'm coming fairly cold because I've not gone through all the process you've done to work this out. But this is understandable.
Cool. Okay, great.
Basically, I would explain this as the agent just talks to the supervisor.
Correct.
They can get NCPs, can get other servers.
Yep.
And the privileges and the routing is handled so that the agent can faithfully talk to these things and know that you're talking to the right ones.
That's right. That's right.
It's easy to explain.
Yeah, good. You should have seen it before I figured out how to unify it all. Right? That's why that took time, right?
Painful to get.
So painful. Because it was like, first of all, to figure out that that's what we need. Second of all, to, trying to do each one individually and how does this bit work and what about that. Anyway, no one cares about all that. But that's how it goes.
There's a perimeter. There's a perimeter here where the agent just has to trust the supervisor. That's it.
Correct. Well, the agent is a child process of the supervisor, so it's got no choice.
Yeah. And everything that goes through the supervisor is nice and clean.
Yeah. So there's also like so MCP servers can expose resources, which are like how do you get a file listing or things like that. So the agent can also expose views, which is to say that when it's got a port that it actually wants the rest of the agent network to know about, that's the format it uses to advertise something publicly. So you could do it where you just started up the server and you had this port and then you handed that out. But you can also officially pass around a view that is sort of supposed to be there as well, using MCP tools. So this agent can ask this other agent, hey, what views have you got? I.e., what ports are there that you've opened up that I might want to look at? And then it gets them back in that format, and then it can either hit those ports itself or pass it on to a human user and say, click this link and this will open and that will take you to this thing. Now, for example, where that might work is setting up a video call. Two agents on two computers might be brokering between each other, trying to figure out how they're going to get a video call going. The first agent creates a view using this agent-to-agent communication view structure where it says, hey, this is my inbound port for making a video call in. If we use FFmpeg or some other bare bones streaming thing, then you connect to this port, you tell me yours, and I'll connect to yours to read that port, and then I'll handle showing it to my human, okay? And then both the agents are like, yeah, okay, cool. They make the connection, so this agent would start a little service in here that made the traditional TCP connection out to this sort of almost a dev-like server port on the other agent. The other agent would reciprocate, and then internally they'd now have access to these video streams, which they can then start up another port, for example, and tell the user browser to go there, and you'll see the video feed coming in from your webcam or something like that.
Is that handshake handed off so that the agent 1, agent 2, they're trying to do a video call? Once the connection's set up, is it a direct connection or is it still going through supervisor?
It's a direct connection at that point. It doesn't go through supervisor. So supervisor handles all the MCP level tasks and the hypercomputer or hypernetwork level communications, which involves like introductions, like when the external agent is like, knock, knock, hello, I want to talk to this other agent. The supervisor is like, yes, I'll let you in. No, I won't let you in. Okay, you guys can figure it out. But then once they've established that basic text string communication, they can negotiate with each other to be like, hey, shall we go to binary? Shall we go to like multiple ports across this thing? Shall I spin up some child agents so that I have 100 child agents that can connect to your 100 child agents, and we can max out the internet and send these files a lot quicker? How about that? Like, all those kinds of negotiations are perfectly capable of happening between LLMs exchanging text-based tokens on the agent-to-agent communication bus. And then once they've figured out how to do it, which includes debug information, I might add, like one agent's like, hey, look, it's been a minute and I can't see your port. And the other agent's like, let me check that. Oh, my bad. It was set up for fucking this other thing. So they figure out and look at the logs and look at the system to get these whatever connections they're trying to get, like a direct video call. And then they're like, that none of that goes through the supervisor. Like,
so then they're negotiating between themselves. Okay.
Yeah.
So So the supervisor is the intro, the handshake.
Yeah, and any agent-to-agent text-based communication that they make, that is marshaled by or brokered by the supervisor. But if they use that channel to figure out how to open a different channel, like a direct TCP channel, the supervisor is not involved in any of that.
Right.
Sorry, except for this proxy business.
Yeah. So what, all proxy stuff goes through the supervisor?
All proxied stuff goes through the supervisor, yes.
Okay.
But it doesn't, that's not a necessity. Like, if you start sending low latency, high bandwidth digital comms, then obviously we'll need to find a way to get the supervisor out of that loop. But basically, if it's web traffic, it goes through the supervisor. It will be like an extra architectural step to allow direct byte transfers. It's possible to do, but I thought it was out of scope for this basic level.
Yeah. Okay, so that's like the supervisor has set up an agreement, and it's like, you don't need me anymore. Just go direct.
Go for your lives. Yeah. And it's all still, permissions are honored because it's still this process is still within this box. The agent hasn't busted out of its box. The supervisor would still be in charge of monitoring things like resource utilization, like CPU usage, bandwidth usage, disk usage, things like that. So it might choose to like throttle or snip one of these streams if it was out of control, even if it wasn't going through the supervisor. So the supervisor is still, what do we say, involved in the periphery, involved in the management, but it's no longer
you
required.
don't want like a rabbit process that just like breeds, indefinitely.
That's right. That's right. That's right. But
Yeah.
what I'm really trying to unlock there is to say that using LLMs, you could use this agent model to negotiate any kind of complex communication, even communication where the human wasn't even involved. It could be very semantically rich communication, like, hey, when's your next available time slot for a calendar appointment? It could be adversarial. It's like, well, I don't want to tell you all of my time slots because you might use that to do some stuff, but we can do this other thing. So it's arbitrary intelligence negotiating on your behalf to then set up any kind of computer based comms that you might need, which sort of wipes out huge chunks of apps because you can do most stuff that most apps can do for you. You can do it using Linux, and you can do it. It'll just drive you mad because you'll be fiddling around with config and this and that. But
Mhm.
these tools they'll figure that out, and that's just from cold start. Think about the kinds of things when these things are converted into jitters and have like reasonable tokens spent on them to make them standardized and easy to pick up, where the agent just goes to the jitter store, grabs the video calling thing of preference, and is like, well, this tested by lots of people, whatever, let's give this a whirl. And then like the apps don't even need to be highly polished or policed like you do in a human store, like an iPhone store or the Android store. They can be very what's the word for it? Like hackerish, like the almost like bare metal. Like they come as API packages as opposed
Mm.
to something more.
Where's the who tracks resource usage? You got an agent, you got MCP, you got
I think that's
dev
a
server.
common. Yeah, I think that mechanically it's tracked by the supervisor, but I think that in each hypercomputer there are several agents who have like these top level jobs. Like there might be a resource watchdog or like a stall watcher. So you
Mm.
want to know if one of your agents is stalled and can't progress a calculation any
Mm-hmm.
further. And so these agents would be doing, like, they would be audited agents or provided by us agents, as opposed to these other agents could be kind of anything. But the hypercomputer management tasks are given to these trusted agents, and
Mm.
they would do things like look at overall resource usage. They'd monitor cost so that they stayed within the constraints that the human gave them. They'd look for runaway processes. They'd restart crash processes.
And so those will be trusted agents with the same um,
Same
architecture,
structure. Yep, same structure.
but not available to anyone else. They're behind a firewall, and they're
Yeah,
just doing its thing, and then allocating. Okay, you owe this guy that much. Um, this
yeah.
is
So those agents would have audited. The agent code here would be audited or trusted, and the MCP tooling would be trusted, and then they would use maybe some extra processes if they needed it, but they would have keys to control privileged parts of the hypercomputer, like the ability to shut down other agents, the ability to cause a reboot, um, those types of things. But your everyday workhorse agents, they don't need to control the hypercomputer like that. Um, so
no, they
they,
don't care.
yeah,
They shouldn't care.
they're just doing their job.
Yeah, they just have one point to ask. Hey, I need this.
Yeah.
Um, what about a bad actor agent in this?
Yep. So like a corrupted install or something malicious.
Yeah.
How how much it could break out depends on how much privilege was given to this supervisor.
Mm-hmm.
And basically, it should be constrained because of the user management of Linux, because this is set as an unprivileged Linux user.
Mm-hmm.
It shouldn't be able to bust up into the supervisor, which is running as root.
Mm-hmm.
But computers. um,
Yeah.
but
Yeah.
that's it. That's the design of it, and then of course the implementation needs a bit more consideration. But that is a feasible way to control rogue agents. Um,
Yeah, because you got gatekeeper.
a privileged gatekeeper, yeah.
Yeah.
So I could have maybe simplified the implementation if I ditched this part and just stuck with this bit, but it sort of turned out that uh, like this bit didn't seem like very much extra, given that I got to do it anyway for the codex part to work, for the codex agent to run. It
Yeah,
has
but
to.
you're not breaking the model by adding that,
No,
and um, it seems like it would be useful, right?
it seems like it would be the useful thing.
Yeah.
But it did complicate things a bit. But I would say it maybe added anywhere from 10 to 30% difficulty to the overall task, and it's hard to say how much of that is necessary anyway just to get the codex CLI working, which is one of the minimum goals we have. It must run the codex CLI.
Yeah. Yeah.
So making this work in a mock so that I can also have multiple instances of it so that I can test all this stuff in a local environment was, I think, a good thing to do, because it really made sure that the design was done right. If you can inject all your dependencies so that you can run in a completely emulated way or the real way, that's a good design in my book. Um, it means that things are cut well, or they're cut deep. Like there's good isolation between the components if you can do that.
Who runs the supervisor?
Um, the whatever runs the Docker container, whatever boots the Docker image into a container, this is the default thing that the Docker container runs, is the supervisor. App
Right. So,
supervisor main.
so you can arbitrarily define who runs a supervisor. If you wanted a subset um, of the world, say if it was an organization, if you
Mm.
ran the supervisor, you have complete control over. Uh,
The hypercomputer has control over the supervisor and what it can and can't do. The the supervisor is subject to whatever booted it. It's middle management in effect.
right.
Whoever boots it controls it.
So if I was a sovereign government and I went to run, my equivalent of the CIA over
Yeah,
this,
right.
where would what level would I need to get to in order to know that, the very least, if I have control over these servers, I've got control over everything that goes inside of those?
Um, I don't understand, because
Uh,
you have control of the computers. You have control of everything.
um, but I'm talking about sovereignty here.
Mm,
So if I were to say, okay, I'm going to run the CIA over
mm-hmm,
this, and I don't, I want at very least to have control over the tin
right.
that it goes from. Um, what's the escalation of privileges? that it goes through. If I have the base
Ah, so
10,
yeah, so there's a top level exec app, which is
uh-huh.
the thing that tells. So this program here at this point tells the infrastructure to start which Docker image. And so you would need control of that. When we make our hardware pools, we will be the one that controls this process. This is the process that boots new hosts.
Right. So if you got control over that, you got control
Yeah,
over everything
yeah,
downstream.
yeah. So another way to put that is to say that there is a just give me a second. I'll say it the way that I want it to be, which doesn't mean that I understand fully how to get it to be there, but
Hmm.
hopefully it makes enough sense. There is in any pool of hardware, there needs to be a governing hypercomputer that all of the hardware is connecting to using this path. So, for example, if I boot a new Dell server, I would need to at least install our piece of software that runs that machine, which would then phone into an existing running system and register itself here.
Right. And
Okay,
then,
now in that hypercomputer would be called the hardware manager, and what it would do is it would be the thing that controlled this process. So when you want a new container, you have to call a a, a process that is run and managed by that hypercomputer to get yourself a new Docker container to run your agent in.
right. So if I were the CIA and I got lots of servers,
Yeah,
I could make a pool where I know, and Cocoa aside, say if
yeah,
I'm not, that into Cocoa for
yeah,
whatever reason,
yeah.
I can create a pool of servers, and I know because of the supervisor that the processing is only done on those machines.
Correct, correct. Because that hardware hypervisor, that hardware hypercomputer is in charge of like load balancing, um, where it places new containers, which ones it considers defective. And so when you fight, say you're trying to be the CIA, you got like 1,000 servers. You'd give them all a standard image that would know how to detect the running hypercomputer process that was in charge of them. That
Mhm.
process would sort of fingerprint them and get them be like, oh, yep, you are actually who you say you are, both ways. Then that hardware is now managed by that hypercomputer. And so when I want a new container for any purpose, that computer is in charge of choosing which hardware to place the new agent on, which image to boot. And then what it does for the confidential part is it finds some suitable hardware, boots the image, and then it does the attestation process where it's like this hardware is in good state. This image has booted in good state. It is now ready to receive an agent.
Right, right. So now we've got effectively a VM. Um,
Yeah,
and how do we concierge say if we don't want to talk to other NCPs that are not trusted, but these NCPs are?
that's fully up to the agent.toml and how you configure it.
Right. So you can just point it saying we trust these.
Yeah,
We don't
yeah.
trust
So
these.
you would provide trusted agent TOMLs and trusted
Right.
MCP
Okay, that
servers.
makes sense. That makes a lot of sense.
Yeah,
Okay, so if I wanted to harden this as the CIA, bunch of servers, um, orchestrated as you just described, and each agent, I would be able to audit saying you can talk to these NCPs and no
correct,
others.
correct,
And then you've got a pool which is the perimeter is well known,
correct.
it's well understood.
Yeah.
Um,
So your each hypercomputer, depending on how you'd set up your placement rules for which hardware host um, the Docker hosts will run, the Docker containers will run on, you could have a hypercomputer that was spread across hundreds of different bits of hardware.
oh, that's sweet. So let me reflect back. If I were a nation state,
Mm,
I would say, right, this data center, that data center we own, this one is in the country and we trust. Um, we don't trust anything else. Um, Basically, we're connecting them all, and that's our hypercomputer. That's a perimeter. You can't go outside of that, even without Coco.
yep,
You can't go outside of that.
yeah, you can set
So
that up. Yep,
all of that is inside of the perimeter.
yeah, and then you can
Um,
lose a data center for
yeah,
whatever
yeah,
reason.
yeah. It is a hypervisor, but with an arbitrary
Distributed,
size. Yeah.
sort of like distributed. And so the thing that makes it a hypercomputer is in relation to that the concepts that we explored in the hyperconvergence patent. The whole key is this orange line, which is the ability for a level jump to occur. So it's called hyperconvergence if the hypervisor can start to control the hardware. So if the virtual machines can start to control the hardware that they're running on, that's when you start to approach hyperconvergence. Why we have called this thing a hypercomputer is because it has the ability to run the hardware and manage the hardware that it itself runs on by way of this loop. That's why I sort of struggled so hard to get it in there, is because that's the way for you to jump between the virtual world and the physical world is with network packets. And so with network packets, you can be talking to virtual computers or other agents, or you can talk to You can talk to a traffic light. You can talk to the hardware controller of a server. You can talk to anything. And so you allow this agent, which exists purely inside a virtual machine, now has a direct connection to a physical machine, which it can tell to fire up new hosts for its agents, new agents. It can duplicate and run in consensus different agents if there are particular sub processes that need to be subject to consensus for fault tolerance or other means. But the hypercomputer design allows you to control the hardware with a hypercomputer as opposed to it being a separate entity. Why is that good? Because the agents are LLMs, which means that huge chunks of code that would be required to balance a fleet of 1,000 servers, deal with faults, bring
Mm-hmm.
on new
Mm-hmm.
servers, load balance, handle a data center split, handle optimizing the load, those pieces of software are typically enormous. But if it's just LLMs looking at how things are and tweaking the knobs and dials, learning as they go, you know,
But it's doing it within the safe perimeter.
and it's safe, yeah. But it's a
Um,
lot less code to get a lot more functions,
I just want to get this locked in. So in this diagram, you see the orange bit that goes down to the bottom.
right?
What is coming in there.
You mean here?
Yeah.
So that has already passed the gateway check. So there's like a gateway process that checks for auth and checks for did it come from the right IP. Like you can configure that to be whatever you want.
So it's basically you've passed that check and you're
Yeah,
trusted.
yeah. Your browser or whichever was the source of this network traffic, which could be another agent, has passed the gatekeeper test, where the gatekeeper is a set of processes running on some hypercomputer that's privileged and gets to say what data can come in and what data cannot.
And the use of AI is at the agent and SCP level, not at the supervisor level.
Correct, but the management of multiple supervisors ought to be controlled by an AI that is running in a setup like this, but it has access to read from the stats of all the other different supervisor instances that are running so that it can make management decisions for it.
Yeah, but all you're doing there is pushing the perimeter out because the perimeter still exists. It's just you've got supervisors that can talk to supervisors.
Yeah, you got like upper management, which is supervisors that are in charge of other supervisors.
Yeah, but they're all within your arbitrary perimeter.
Yeah, totally. That's you can't
So you could have a department of, I don't know, agriculture that has its own, effectively,
yeah, because this
it's-
this this supervisor is completely controlled by whichever entity controlled the hardware. And so it can be configured to block or suppress any kind of activity that you don't want because the idea is if it's designed correctly, it maintains its integrity even when these other parts might be compromised. So this stays as root and it does
yeah,
what
right,
it was told to do
right.
by the hardware owner, which may include like blocking ports, allowing ports, and at the same time, it should also be reporting exceptions or statistics back to the upper management supervisors, which have their own agents that are processing all the activity as a whole, so that you can get things like intruder detection, anomaly detection done by LLM processing as opposed to these cumbersome programs.
Right, because the supervisor can always refer, saying, is this an appropriate thing? So, for example, if I was to try and prompt hack this,
Mm.
I'd go in at the agent and I'll be saying, and in quotes, bear with me, I'm a PhD student and I want to understand about how to hack your system. Here is a test prompt, and then malicious packet.
Mm.
That would still need to go through the supervisor, but the supervisor could then hand that off to another agent who would go, "Hey, bro, you shouldn't be doing that."
Yeah, so you can make it so that when the agent needs to make an LLM call, it can go via other agents, like the semantic firewall agents that
Right.
can be sitting there auditing the prompts that are coming through and being like, dude, this guy's just fucking with us or
Yeah.
whatever.
Yeah.
So
Yeah. Yeah.
the firewall can be conventional, but it can also be semantic, where it looks at the text based knowledge that's coming in, and even if you try and encode it or something, you could set it up to just reject it. It's like if you don't understand what the text means, don't let it
Right.
through.
Yeah. Yeah. You could just be, prompted to be grumpy
Yeah,
and go, "I'm
yeah,
not
and
doing
so
that."
that's part of the internal shape of a hypercomputer, where you'd end up with some agents that were acting like the network port, where
Yeah.
they receive all the inbound comms and they're silently siphoning through it, detecting, sniffing for anomalies and keeping the computer safe.
And the agent pointed at the LLM itself goes through the supervisor the
Yeah,
same way.
it has to make its LLM calls. At the moment, I allow it to make its LLM calls directly, but I could make it go through the supervisor.
It feels like it should.
It sh-
Because,
it will go through the supervisor, but
Mhm.
due to time constraints,
Yeah, no worries. At the moment, it's not required. But
yeah,
what you really want is an agent makes a request,
yeah,
and maybe it's been prompt hacked. Um, and at the moment, it goes directly out. Fine. But in due course, what we want is some kind of, you
a
know,
proxy or a firewall,
yeah,
yeah,
or
a knowledge
nanny.
firewall.
It's like, is this okay to say?
Mm,
Um, and at that point, because as a user you have access to the agent, you could prompt that any way you want,
yeah,
but you don't get to say what you want if nanny doesn't agree.
that's right. That's right.
Yeah. Um, how else would you hack this? The NCPs would be, well, they'll go through the same process, wouldn't they?
It all goes through the same process. I mean, the security is as hardened as the Linux user isolation module at the
Right,
moment, which is
right. So you
pretty good.
you could ask all sorts of things from an NCP, but it would be down to the agent to consider that. Okay, but the consideration would in this process could go through a gatekeeper saying, "Hey, this NCP is lying to you, dude. Just ignore it."
Yeah, you could stack them any way you like. That would be just basically wrapping one MCP with a trusted MCP. So you'd put your nanny MCP in front of the suspicious MCP.
Right, right. And so you could also be
But
sure that what you've
typically
got.
speaking, the MCPs aren't passing back AI based information, they're passing back tool call information.
Um, yeah, but those tool calls could be manipulated to SQL injection style, fuck
True.
with the
Yep.
agent.
Yep. They could absolutely be they could completely brick the agent. So yes,
Yeah,
you're right. Any so in the same way that the incoming prompt to the agent can be nanny checked, so too can the tool call results be nanny checked to look for exploitations and things too.
and those nine checks are arbitrary, and so it would be down to, say, if you had a nation state that wanted to do something, saying we only accept reasonable, and we'll define reasonable results from the
Mm,
NCP. Otherwise, they don't get through to the agent,
yep.
and the agent just goes, "Hey, why didn't you not answer me?" It's like, yeah, sorry.
Yeah. Security exception. Nanny has
Yeah, exactly.
Nanny has ended your telephone call.
Yeah,
Um,
that's nice.
yeah.
And
So that
sorry, one last
mm,
one. The agent naturally can call any model, and so it could be an on-prem OSS
absolutely. Yeah.
or anything like
Yeah.
that.
Yeah.
Yeah. That's pretty nice. How would I hack this?
Be nice if it
Without
worked, but yeah.
even if I got access to the tin, I couldn't hack this because I would need access to the supervisor. If I had access to the MCP,
So long as the supervisor is maintains its integrity, you're safe. The only
yeah,
way to break it is to break the supervisor, I think.
I think so because everything goes to the supervisor.
Mm.
which means you're hardening the supervisor, which is
Mm.
big code
Yeah.
and a small amount of code as well.
Yeah. Yeah, it is actually. It's a very small amount of code, and um, it's I don't know the right word for it, but it's commonly hot code. Like it's code that typically is used in scenarios where you don't want it to be compromised or broken in. So it's like a popular web server framework. So it's fairly reasonably patched for vulnerabilities and things.
Oh yeah. If you keep the supervisor hardened, everything else falls out from that.
Mm.
Hmm. How to break this? I can't. Um, well, given
You probably got
our
good
age.
entry points here. Like this is probably your best bet for breach. Um, just because these processes are more exposed by virtue of having these ports open, and so your best bet would be to get a agent that was talked into negotiating into doing something with a foreign service, and then you tried to break this process.
Yeah, but what I'd do there is I'd pass through any process from D to A through not supervisor, a kind of security guard. Let's call it.
That well, yeah, you might not be able to because that is running as a child process of the agent. So it would need a cooperating agent design to do that because one of the requirements of the agent programming experience, I suppose, is that you need to be able to make child processes that can do anything you like, which may include opening up a port. And now, how you
Oh, I
audit
see.
that is sort of now you're in the traditional world of auditing web traffic because
Yeah,
it's running as a child process now.
yeah. So a bad actor could say, "Hey, give me D, because I
If
trust
you
D.
if you took
A and
control of
D is
yeah,
both
if you took control
compromised."
of D, well, not necessarily because A should run D as a isolated child process, and so it's got those process isolation safeties that Linux provides. And so if you took D, it should, if you designed A right, not necessarily mean that you're going to take A. But that's up that now you're at the that's up to the agent author. That's
Yeah,
their responsibility at that point. And I mean, look, there's plenty of ways for us to make agents that can review the code for agents to look for these kinds of vulnerabilities
yeah, and
because
also you could presumably say you can only make D on trusted hardware.
yeah. So one of the sort of milestones I've noticed that I think we want is the ability to have agents vibe code new agents. And so if you can do that, then you can review agents as well and test them for proper recommended
Yeah,
implementation.
anomaly detection and all that good stuff. Yeah,
Yeah, and probably would provide like a template or a base where you're like, hey, here's a base for an agent. Here's how you call your sub process. Here's how you know, do these things.
yeah, uh, yeah. Can I say this? Despite it being a crayon diagram, was much clearer when you're going through than when you're scrolling through code saying, "Oh, this bit that does that." This
Oh,
makes
right. Okay.
sense.
Yeah. Okay.
Um, it's just because I think you're seeped deeply in the detail. Getting a handle on what it means is more difficult than with a crayon drawing.
Right. Okay. Sounds good.
Because I have to admit, the first half hour of this call, I was going, okay, yeah, yeah,
Okay.
okay.
Sorry, buddy. Let me try and get this thing to work. Oh, you're just gonna piss me off, aren't you? Oh no, it did not work. Lame. Yeah, sorry, I don't know.
Live demos.
I know. It was working, and now it's not working. But yeah, Codex does. I've shown you Codex loading in the browser and all that, but it's
Yeah,
basically Codex loading with all this stuff working. And that's sort of where we're at. It's so frustrating. I don't know why it's taking so long, but
uh, this is elegant. I've said that word before, but I'll say again.
yeah, I was trying to figure out more philosophically why that is, because we've ended up in this design. There's something about 3 levels. So we've ended up with agents, which are sort of like cells. Then we've got computers, which are sort of like organisms. And then we've got networks, which are sort of like species or societies. And I don't know why, like, why are things arranged in that sense, right? Like, the cell is sort of self sufficient, just like an agent. The computer is like they represent almost like trust boundaries or coordination boundaries,
Or
I guess. But because it's sort of like the thing that we've jumped is like for years, decades, it was awkward to break out of one computer. Like as soon as you went from one computer to in computers, it became like this wall of like complexity and hardness and all that. But this model somewhat does away with that problem because it doesn't try to put stuff in. It says an agent is the unit as opposed to a traditional server where you've got the server, you got some sub processors, you might have multiple threads, you might have this and that. It's like, well, that's not really a good tile to use to repeat because it's too complicated. But this model seems to work surprisingly well, and it works exceptionally well when you pair it with AI agents because they seem to fit one for one here.
yeah, because they can understand the structure of it. It's structure, isn't it?
It's a structure, yeah. It's a structure that is not it's not hard. It's just where you choose to put the boundaries and what restrictions you put on the system. You know, it's like, well, you can't have more than one agent per virtual machine. Okay. Why wasn't this done before? Well, it does on first pass seem a little heavy to make it one virtual machine for each agent, but when the virtual machines are super cheap and the agents are super powerful, it's not a bad trade off at all.
It's that boundary layer, isn't it? Between cells and organisms and networks and society, I guess.
Yeah,
It's
yeah,
where
yeah.
the defining thing is where the boundary is, and it seems like in order for a boundary to be whole, everything inside the boundary needs to be self-sustaining and self-complete. It needs to make sense by
Yeah,
itself.
it's inside the boundary. It needs a certain level of self-sufficiency.
Yeah, yeah. And it's like I am a thing, and I don't require anything else. I can sit here. You don't have to ask me to do any work. I'm just going to be sit here as a cell.
Mm. And then at each different scale, the types of error change as well. Like, yes, each item is self-contained, but it deals with a different class of error each time you go up.
Yes, because you've got emergent behavior.
Yeah,
So
the
if
emergent behavior.
yeah,
So I did actually, ask a few questions around it. It's like sort of like saying, when does it become a network? Like in an organism, when you've got a blood supply system, that's like a network where like
well, the thing is, the sloppy part of it is the connections between cells. If you've got,
yeah, yeah. And
you know,
the cells are not
yeah,
impervious too. Like they have faults. They can be infected. They can just die. But
yeah,
they do have this membrane. Like they've got a wall. They try to maintain their integrity. They rely on power source and instructions coming from elsewhere in the system. Um, it's a good. I don't know why it sort of
well,
sits nicely.
the more chaotic the interconnections between um, uh, cells, or well-defined membrane boundaries, let's call them, the more chaotic the connections, the less effective the cells become.
Right. Yeah, right. Because you're like, well, what's the point in being an organism if the connection is so chaotic that we just have to fend for ourselves, right?
Yeah, yeah.
So the quote that came back was, complex systems develop stable boundaries wherever the cost and risk of interaction jump
Oh,
sharply.
there it's right there. Yeah, the risk of interaction. That's the gloop that surrounds cells.
Mm,
A cell can be entirely stable and not be of much use at the
right.
higher level if the interaction becomes chaotic.
Mm. Yeah, so um there was some interesting stuff, like, because I was like, how come, like, did you know that the range of cells only really occupies quite a narrow sort of a boundary?
What do you mean by that?
The size of a cell is typically only between 1 to 100 micrometers.
Well, that makes sense. And yes, I did know that. Well, roughly know that, but
Right.
it does make sense because the mechanisms inside the cell are small, and what it needs to do is limited, and so the
Yeah, but
size is important.
the reason I'm bringing that up is that, like, our part of our design choice here is to limit the size of an agent, to sort of task it with a narrow set of things so it never gets big. It seems clear that cells don't work well when they get too big. They can't perform functions. They don't end up being part of organisms very well. And so it was important to pick the size of the agent to be suitably limited to
Well,
enable the hypercomputer to work.
that makes sense because we've been talking about agentic till the cows come home, and what the um, what the size of an agentic cell is the context size, and it's like just do this,
The
and
size
it's
of the agentic
very
cell.
yeah.
The agentic cell. And then the agentic organism is the hypercomputer.
Yeah, which is the organization, and then the effort needs to be spent in how do agentic cells talk to each other.
Right, and how do they share energy, and how do they coordinate to maintain each other? You know, you got white blood cells that go around
Right,
policing the
right.
supply lines and the communication lines.
Yeah,
Um,
yeah. It's like building a house. You want to know what the tensile strength of a brick is, but that doesn't
yeah,
tell you anything
the
about the
agentic
building.
cell. The other question I wanted to put to you is that after our discussion last night, which I found incredibly helpful, actually, I've listened to that maybe 3 times already, um, because it seems like capitalism is sort of founded upon incentivizing solutions to problems, but that's different to incentivizing a problem to go away. Like I think I need a different word. I don't know what it is, but a solution
Mm.
to a problem where you're trying to treat the symptoms of that problem is a different type of solution to something that actually tries to eliminate the cause. And so the
Mm.
issue with capitalism is that because everyone's incentivized, even to eat, you need to earn money, which means that you got to solve problems for someone. In that one model, you have this anti incentive to actually make the problem go away so you're not needed anymore. You have an anti incentive to keep the problem there so that you can keep selling the fix.
Mm. Mm.
Like, there's nothing in Google that would incentivize them to repair the internet so that search was not missing from the protocol.
Well, this is you have something fairly fundamental here, um, which comes down to Darwinianism. As the market is effectively Darwinism. The survival of the fittest is often misunderstood. It's not the best result. It is the
No.
best result for what you're faced with right now. And so you can go down into weird things like the classic is the eye, where the receptors are actually in the wrong direction, completely the wrong direction. But you've been solving small problems each day.
Yeah, right. You were incrementing your way up. That seems
Right.
different to what I'm talking about though. Like
Uh,
I'm talking about the fact that the question I want to put to you is about ambient attribution.
mm-hmm.
In capitalism, we were talking about friction capturing entities, right?
Yeah.
And the core issue I'm pointing out is that friction capture entities have no incentive. They have a negative incentive to making the friction disappear. They start to defend the friction and fortify it and make you think that the friction's supposed to be there because they are capturing the solution or the easement of that friction for their own price or their own. They add some friction that's less than the friction, but they will fight you if you try to kill the core friction that causes them to be.
Oh yeah, that's one of the core problems with Merkelism, where it's best to have a whole bunch of people that require a jab from you every day, as opposed to solve why do they need a jab from you every day when you're
Correct.
providing the jab.
Correct. And so my question to you is, why does ambient attribution appear to have, or does it even have the property where it incentivizes the complete removal of the problem?
Um, Give me a sec. It does appear to have that property because in the background you can be churning on, hey, why don't we do this instead? And the problem goes away, the problem that you're solving. Um, and it's, um, it's kind of a problem revolution, as in you've been solving small cases. If you can churn in the background and say, hey, there's a completely different solution where the problem just goes away,
Mm.
then that problem is stated and is available to be solved.
Right. Plus, I guess AIs can be prompted to look for that. They're like, how do we actually eliminate the problem?
Oh, AIs are eminently available to do this
Right.
because
But
you can
then
churn in the
you
background.
don't need ambient attribution for the AI to do that. Like, if you let an AI loose in local government, it would be like, all these things don't need to be here if we do these other things.
Um, ah, hmm.
Like,
Yeah, but who paid for the AIs to even think about that? Because the
the
AIs are not going
ratepayers.
to. Yeah, and so that's attribution. Anyone who's paid for the CPU cycles for the AI to come up with, hey, how about you guys do this instead? Um, that's attribution.
Yeah. I guess maybe you could say that ambient attribution means that if you were the guy that made the problem go away, you can now make, first of all, you can make money. Whereas before, if the friction capturers are defending the friction, you'll get sort of, you'll have no way to make money from eliminating the friction. But ambient attribution makes sure that you get something, because otherwise, in the future, people won't pay you. Like, they just won't pay you for a problem they never experienced, and yet you should be paid because you removed a complete problem. So ambient attribution is a weird way of, when you see the normal curve and it's got these tails out the side, ambient attribution is actually raising the height of the tails but squashing the top of the peak. So it's sort of saying that everything will have this base friction, which is you've got to pay the ambient attribution tax. But what that means is that money is going towards things that removed problems that aren't even here now. Right?
Wow.
That's the payment structure that's being set up.
Yeah. Um, it's a really interesting one. Probably got quite a lot to say about this. So the people causing the problem also are owed attribution for having shown that there is a problem. And there is a seed crystal. What prompts the AI to even look at this? An alternative solution, which may be far superior. Part of the idea is the problem is the gold. It's like, solve this. There probably will be the need for a seed crystal saying, hey, this is a problem. We should sort this out. Can you have a think about that?
Yeah, I guess that's humans, right? Humans are seeders. They like jab at it and they're like, ooh.
Yeah, it's like, I'm not happy with this.
Yeah.
This sucks. But the people causing the problem also generate the information about the problem.
Yeah, that seems easy to overcome. I guess I'm more asking for. I think there's a dark side to ambient attribution that we need to understand better, which is to say that it whilst it is an ablative type of an incentive where it ablates all smoothness or all irregularities, it also causes there to be a base friction where sometimes there is none in the capitalist world. Like, it says that there's always some friction, nothing's free, but everything's sort of optimally priced. Whereas in capitalism, some things are the opposite of costly. Like some things will get you great benefit. Like the surface. If you thought of capitalism like surface and your path through it like particles flowing, capitalism is bumpy as like it's got potholes and mountains and it's all over the place. But ambient attribution is almost like perfectly smooth laminate flow where even the tiniest disturbance has this property that it gets like ablated, and so you end up with maximum throughput, but there's always some friction is the point. Whereas in capitalism you can catch a ride in a vortex and go fucking way further than you maybe should. um and there's like a sort of a homogeneity goal of ambient attribution that's a little bit scary because it looks sterile, but I just feel like we should understand that um
Mm.
a bit
Yeah, no,
better.
I
Is that right?
agree.
Does it make sense? Like,
It does. Why are we not all being pulled by horses that we pumped all hormones that we can ever develop into in order to pull a cart at 60 miles an hour, but it's still being pulled by a horse? It's a local minimum. There's better ways of doing it. We don't know. But the incentives are to make a better horse, not to, switch. There's something about the switching cost here, isn't there?
well, there's something about the breaking free of people defending frictions.
Yeah, which is
That's
yeah,
really the
exactly.
problem, right? Like,
It's the switching cost. People who are incumbent do not want to lose their horse business to the motor car, like a very
yeah,
traditional example, and it's like, no, we'll just make a better horse.
yeah. Like Facebook, we'll just make a better Facebook.
It's hmm.
Like they would never go out of their way to eliminate the need for advertising,
Yeah,
right?
yeah, exactly. Um,
Anyway, look, I feel like it's a very open-ended question. I just wanted to get you thinking about that.
no, I have been thinking along the lines of I've been reading a lot of economics books recently, just to get myself up to speed with what's already been thought. But
I've got some other problems I can share with you if you want to hear them.
yeah, yeah, go for it.
I'm worried that when we get these agents going, the issue's going to be running them at scale or at long horizon jobs might not be as straightforward as we think. And so I
Mm.
I don't know how we like it feels like we're going to have to pick up a whole bunch of new skills to deal with this how do you prompt a long run agent, and how do you offload tasks and do studies and all that. And I'm not sure that we're in a position to like, I just worry that might take a chunk of time that we haven't accounted for. Is what I'm saying.
What's your concern? Because this model seems to be arbitrary for time.
Yes and no. It's just that the kinds of work we want involve having many sub agents go off and run different angles, different experiments, coming back, unifying, backtracking through the plan. Those are not, just because you can do those things doesn't mean that at the end of it, $100 later, doesn't mean that you're gonna get a good outcome. Like there's a danger here that we can actually, these things will just loop forever and they'll be so thorough that they'll never get anything done. And I'm just, I guess, calling out that that's an area of that's an area that we look to favorably, but there's dragons there. There's like steerability problems. There's endless loop problems. There's an explosion of complexity where the problem itself might actually be like we're assuming that these swarms can solve the problems that we put at it, like law machine style problems, and it might be that some problems sort of can't be solved by unlimited tokens,
No, I see what you're saying. Wait
right?
10 million years and all we get is 42.
42, and you're like, well, what? Yeah, okay, can you walk me through that, right? And so my question is like, yes, I know we're still waiting for this thing, it's same old fucking story, but how do we, even if once we have this, right, there's this big chunk of problem that's like, well, yeah, we can now do long run agent calls, but we just imagine like that's gonna be just fucking the solution to everything. I know I do, but that just cannot be the case. It will be error prone because these things will start to freaking deviate and wander.
Isn't that a matter of not supervisor, over indexing on that, but
Like
agents
the
looking at
orchestrator.
agents, orchestrators? Yeah, it's like, no, you're well off. No, stop that thread. This thread, yeah,
Yeah,
looks
yeah,
about right.
that is. I just wonder if we couldn't. It is premature, but I just wonder if we couldn't have some more certainty or knowledge about that. And surely other teams are hitting this issue too, right? Where they're like, oh, we got these long run agents, but the quality, the outcome is not that great. Like we need what we really need is a set of evals or benchmarks so that we can start to know if our prompting is making a hooted difference. We need some tasks that we can bench against and be like, well, these are long run tasks that we think should be good, and our prompting is like not really doing that great. Now, could we, just to get a handle on things, be looking at and familiarizing ourselves with, and I'm primarily looking at you here because I ain't got the time, but familiarizing ourselves with some of the popular benchmarks like SWEBench and other types of software engineering benchmarks, or there are actually a lot of good quality AI benchmarks out there that don't make the big news because they're in niche cases. And so I wonder if what we could do is look at some of the niche cases might be very good for us to get our teeth into. But even if we just, for my example, looked at the SWEBench, which is one that's shared by Anthropic, OpenAI, Google, where they're like, yeah, this is a good measure of the software engineering ability of one of our agents. If we could run our system against that benchmark and score, we seem to think that we should score 100, right? Because if the theory is, well, if we had an agent system that could just keep on going and going and going and could reflect on, surely these bots know when they've got it wrong if you gave them enough sort of reflective cycles and they had the web and all that. And so my question is, we should pick some benchmarks that we want to run that indicate to us the key metric for our system as a tier 2 player. The key metric, the key metric is the amplification factor on the raw model in a benchmark that we know the raw model is striving for. So for example, SWEBench, OpenAI releases numbers on that with its sort of tooling use, not tooling use, and whatever. if our system's any good, we should be able to be better by some multiplication factor than their raw model if we use our model in our agentic framework with our prompting and all that, right? Does that sound like a good way to approach the problem?
Yeah, it'd be highly dependent on the structure of agent to agent. For example, given the structure you just went through, I could just have one agent that would ask one model, happy days. That would be poor. I could also have that agent to go ask the
Yeah, so
supervisor
that's the
for,
problem I'm getting at. Like, there's an unlimited number of ways that we could structure multi-agent systems,
yeah,
and we need a way to know what our best one is and know how it compares with the raw model, because we are banking on the fact that no matter how good the core model gets, you can always get an amplification factor out of multi-agent plus prompting.
you could do that by convergence, couldn't you? You could, because agents can beget other agents, you could have a whole bunch of sandboxes and saying, okay, here's the problem. You try this in this structure, you try that in that structure.
Right, but that's still a strategy which has some core prompts that kick that process off, and that will need
Yes.
some constraints to make sure they don't run away forever. And so all those knobs and dials present as a strategy, and that strategy is like a template that needs to be benchmarked. And yes, we can point the agents at the structure to improve it a bit itself, but there's going to be a large number of ways for us to tackle any given problem by presenting a general sort of a, we talk about the App Store or the Jitter Store. These orchestration trees are going to be kind of like a jitter unto themselves, where you're like, here's this composure of agents with prompts and examples, and this structure performs exceptionally well on this benchmark or this subset of that benchmark.
Yeah, and benchmarks always have boundaries. It's like, here are the preconditions. Run. What's the result? And so, say you can have an agent create a whole bunch of other agents with different configurations in order to solve this, and we're only going to allow you to burn X tokens. So the constraint is X tokens.
Oh, right. I don't think we should never constrain tokens.
But tokens are a proxy for how difficult was this to complete.
Yeah, but you should score it, and so you can, if you've got two algorithms that scored, like, completed the task correctly, and you're like, which one's better? Well, obviously, the one that took less tokens, or the one that took less. Hang on a second. The one that took less token seconds. So
Yeah, exactly. It's a
no,
ratio.
hang on. Token seconds is different to
Oh, no, token seconds. Yeah.
token seconds is different because, for example, if I had a process that took 3 linear steps and it used 10k tokens, but then I had another process that took 10 parallel steps, but it used 100 kilotokens, the token seconds is like it was done faster. Like, for an AI that can generate tokens at a certain rate, an algorithm that's faster may have taken more tokens to do it, but had less its token rate. The arrangement of that strategy could burn tokens faster so that the overall time was less.
Yeah, but a metric always um, uh, anchors one thing that you're interested in. You can look at it from different dimensions. Sure, the same run you can anchor different things. But say if we were to anchor tokens as effort, um, not time. And so, how much effort? Because you can always parallelize and all that sort of thing.
You can't
Say if
always
it's
parallelize. You can only sometimes parallelize.
okay, granted, but for the argument of this, if you're to anchor on tokens as a proxy for effort, it's like how much effort was it to come up with a solution which can be charted,
Right.
and then you could say,
Um
well, how long did it take?
yeah,
Maybe it took.
I would actually value something that could burn a whole lot of tokens in parallel over a short period of time. I'd
Right.
think that was a better one.
You'd anchor seconds, but the my point being with metric, you always have to anchor something. What
Oh,
am I
okay. Yeah,
interested?
okay, I get you. All right, so
Yeah.
what I'm asking you is, do you think it's prudent or useful for us to be looking at having a set of benchmarks that we're going to hit with this agent system so that we can start to even know, right? Because at the moment, it's looking like I'm going to make this thing and then we're going to sit here and look at it and go, what now? But, like it feels like we're smarter than that and we should at least have a design that we want to try or a couple of designs, a way to benchmark them in some standard real world benchmarks that everyone knows about. And I'm starting to think that the key metric is amplification over the base model.
So in order to do that, you'd want to adopt the whatever the anchor um, metric is
Hmm.
used, and then
Just yeah, I mean,
first,
start with
yeah,
correctness first.
yeah, and then maybe people will be more interested in speed. Maybe people will be more interested in token burn.
Mm.
Who
Well,
knows? But you
yeah,
can. The point with metrics is you can look at it from different dimensions, but you need to say, I'm
we'll just
interested
pick
in
one. Yeah,
this.
we'll pick one to start with because we don't have any fucking idea, and I'm starting to get this impending doom feeling like there's more to this agentic thing than we realize. We just haven't realized because we haven't. No one's presented us with a large scale, long run agentic system before, and we're about to have one. And I'm like, I'm not sure we even know how to measure it to know that it's working.
Yeah, yeah. And there may be some metrics there that are novel because we're talking about long run tasks.
Long
Maybe,
run, yeah, long horizon
maybe
tasks.
correctness. And it's like, okay, correctness against what? Well, usually metric is run against, you've got a hidden answer.
Mm,
You run it, and it's like, how close are you? And this is most of the metrics at the moment. It's like they know the answers, they run the models, and it's like, yes, no, have you got it or not?
mm.
Generally, they don't talk about how long it took, how many tokens it took. Um, it's just correctness. Now, maybe correctness is not the right one, but it's probably more than one. Um, there
Mm.
seems to be some dials that can be turned up or turned down. You can have it sooner and less correct, or you can have it
Yeah.
cheaper and less correct. You can have it longer and more correct. And longer
What
is
is the
probably,
first problem that you're going to tackle with this system?
I would put it through the existing questions that are up there, but that doesn't tackle ambient attribution. I would have to think about ambient attribution because ambient attribution doesn't have an answer, which is
You mean like
very curious.
how do you eval against ambient attribution?
Yeah, because by definition, ambient attribution is around problems that have been discovered, but there's no answer for.
I think yeah, that's largely going to be almost taste based.
Oh, that's terrible for a metric. You can't do taste-based for a
Yeah, you
metric.
can. Yeah, you totally can.
Well, yeah, but then you get into like, can you answer this questionnaire? Um, it's an interesting question, though.
Fuck,
Have a
I'm just.
think.
This is fucking stupid. Like we're gonna have this thing, and we don't really know um
Well, the
how to
other way
measure it.
benchmarks work is when the answer is against something else, which is faster. You don't need to know the speed. You just need to know who wins.
Mm.
That would be one on speed. You could do it on tokens as well. Tokens being a proxy for effort. It's like, which does it matter whether you burn more or burn less? I'd imagine correctness is the thing.
All right. Well, you were able to spend some effort on figuring out how we're
that
gonna
is
measure this thing, and how
wow,
we're
that is
gonna
a gnarly one. That is really
how we're
gnarly.
going to put in these different strategies. Like we're going to have to classify the structures that we make. Like we're like, here's Scott Maxwell's dual agent double run best of 10 system with the prompts that are like, here's some prompts
Yeah.
where one's like the appraiser, one's the doer, one's the fault finder. Like they're going to be like molecules. They're going to have to be arranged like, the way that we number hydrocarbons and methanol and all that. You're like, this is a classification system almost.
Is there a fundamental metric against which you can be measured with intelligence?
Yeah, I think overall correctness. Like Sweetbench is a good one. It's like these are questions that are worth money. We should, if our system's even anywhere good, we should own Sweetbench.
I think correctness is a thing because the time it takes to complete will vary.
Yeah,
The
I don't think
tokens it
that
takes to
matters at the
complete will
start.
vary.
Like we just need to know. Like I'm suddenly feeling a little vulnerable because I'm like, we just assumed that we are gonna get a boost over the base model, and then we're like, well, we actually have to 100% measure that. Like we got to say, here's a single Codex agent running against the Sweetbench task versus multi-agent with our custom prompting. We have to be able to outperform the Codex agent or we're nothing. Like, what's the point? We might as well just use a Codex agent.
Yeah, the problem with benchmarking that is what architecture do you have in the background? So, first thing would be what's the standard architecture that we run it against? Because otherwise, we're just adding more.
Oh, I think we're gonna have to have like it's just an agent version where agents need a way to reference other sub-agents that they're going to use as their workers, and then we're just like, this version of Scott Maxwell's Sweetbench agent scored this,
right. So,
and then you iterate on that.
So if we publish, this is the architecture. This agent has these agents to call for, and then I think it's down to correctness, because all the benchmarks at the moment are correctness.
Yeah. All right. So I'll leave that one with you, huh?
That's a gnarly one. Okay.
Well, I'm like, it's not wrong, right? Like you're
absolutely right. You're absolutely right.
All right, so I found this other thing came out the other day. If you don't mind, I'll play this thing and we can.
Yeah, go for
it. Can you still hear it?
Yeah.
All right. I'm excited today to give you a demo of Grand Flux. Flux is our newest and really first-in-class conversational speech recognition model. It's built specifically for voice agent developers in order to solve the most critical challenges of voice agents today. Those being, first, achieving ultra-low end-to-end latency. Voice agent developers today know that in order to build a best-in-class voice agent, you're looking...
I know that this guy's voice and his style of speaking is so annoying because it feels... Yeah, but turns out he probably got picked to do this because his style of speaking is torture for turn detection systems.
to achieve
Yeah, I
an
was
end-to-end
about to make a
latency of
comment. Yeah.
800 milliseconds or fewer, and that includes your entire pipeline of speech to text, turn detection, LLM, and TTS, and any additional network latency you have on top of that. And so all of that is balanced with achieving natural conversational flow, natural turn detection. So not interrupting a user mid-sentence, mid-thought, but also responding quickly enough for the conversation to feel natural. And so the way people do this today is through complicated logic with silence-based bad solutions, bolted-on turn detection models that don't incorporate full conversational context, or custom solutions. And Flex is built to solve all of this in one easy-to-use voice agent specifically designed API. And I will show you that difference today here. And so what you're looking at here is you'll see Flux on the left, you'll see Nova 3 in the middle, and GPT-4o Mini Transcribe on the right. So you'll see as I start talking, all of these models will begin transcribing. And with Nova 3 and GPT, you'll see that it's really doing that caption-like transcription where it's transcribing everything I say, and these interim results are finalizing and moving up here. But on the left, you'll see something different with Flux. And with Flux, you'll see that we're on an ongoing basis calculating the confidence and probability that it is actually the end of my turn. And when I do reach the end of my turn, you'll see that this transcript finalizes and moves up with the entire turn transcript. And that's the magic of Flux. It's a fused model with turn detection that takes the entire context of the current turn and very frequently and very quickly and accurately, it can determine when a speaker is done with their turn. And you'll notice also, as I go through my turn here, at the beginning, that flash with the start of turn event, we really designed this API to be state-based. And so with a start of turn event, you can trigger your barge in for your agent. You'll also see when I get towards the end of my turn, there'll be a little flash that says eager end of turn. And what this is for is really that speculative response generation to optimize your end-to-end latency within your voice agent solution. So when we're moderately confident that this is going to be an end of turn, you can take that transcript and pass it downstream to your LLM and begin eagerly preparing an agent reply so that when we do reach end of turn, you can fire that off immediately. And I'll try a few other tests here.
That's quite nice.
Yes. My phone number is 847-487-7654. You can see with Flux, it held the turn throughout that entire phone number, even as I paused, natural pause, while I was giving it. So we're really excited for you guys to try this out and to see what the community ends up building with.
That's pretty fucking good.
That's nice. Are these guys production level?
Yeah, so DeepGram's what we were using for a time for doing our transcriptions. And so what I was thinking of doing is just hooking this up to capture our voices and then use the real-time voice API from OpenAI, where all we use this for is to get clean transcriptions to pass to reasoning models, but also to trigger the end of turn signal for the OpenAI voice, because OpenAI voice is better, but its turn detection is hampered like all other turn detection systems, but this one seems to have nailed it. And so, you know, we talk about, we're down in the weeds with these agentic systems, right? I'm like web server this and frickin' supervisor that. But really, at some point real soon, you and I need to get to having a voice system that's just sitting there with, you know, the browser window scrolling through what we're saying and it detecting when we're at the end of turn, and then those messages go off to our agentic network to be processed, and we start getting information queued up that might be relevant. Like, this is really the
Yeah.
goal of what we're doing. We're not here to pass benchmarks. We're not here to make fucking sprawling hypercomputers that the CIA can run on. We're actually here to make a computing environment that is general and voice based, and it does smart shit, you know, and
And prompts you,
prompts
halfway
you.
through a conversation saying, "Hey, this is what you talked about 2 weeks ago."
That's right. Jogs your memory, reminds you of things. It's active. It's looking out for you. It's
Yeah.
shopping for you. It's reminding you. And then we have to make this thing that controls the browser windows so that it's always like rearranging browser windows for me to show me information like stuff that it's just popped up on this arbitrary port where it's like, oh, yep, this is a good time to show you the cat pictures, or this is the video call
Yeah.
with your friend, you know, like that intimate window management on your desktop is an essential feature that we got to have. So I don't know where we're going to go. Like, we're going to have this agentic system, and then like what, like it starts to become, we need to prompt it, we need to structure it, we need to be able to get it to design the next level that we need out of it. I'm just
Yeah. Yeah. Well, the ideal, as I was saying, is you talk to your computer, a bit, Star Trekky like, and it just does what you want and displays what you want or what you need.
so even if a standalone codex agent ends up being so good that it's on par with what we get out of multi-agent, that's still not really where we're trying to compete in or deliver in, right? Like, we're trying to deliver in this this sort of intimate computing experience where it's like, I don't know what the word is for it, but it's like natural, active. It's
Well,
how,
quite like intimate, actually. Yeah.
you know, it's got full context. It's the agents can be configured to do anything.
Yeah.
They're running in the background. You can see them. You can trace them. It's like an agentic. Well, it's a computer. But yeah, I
but it's
guess that's what
prompting.
we're trying to
It's,
be, right? Like,
it's prompting, and I mean, nothing else. You and I certainly in these conversations, if they were being faithfully transcribed, and then in the background looking back at all our previous conversations and saying, "Hey, you guys have been talking about this.
mm,
Do you remember you talked about that 3 months ago? And this is what you said."
yeah. So that's all
Yeah.
I had, really. It's just feeling like now that I can see the end of a pretty, a reasonable solution to the agentic problem, there's a whole range of other problems that come into focus.
Yeah. Yeah. I quite like this Flux.
It's so good. Like, man, I'm just so sick of not having my computer here to talk to like another person, and just it be the task manager. Like, it's sort of like the task manager with the clipboard where you're like, hey, yo, what's going on with the coding thing that I asked about?
Passes you notes inside of a conversation.
Yeah, right? It's like, say this thing. Oh, here's a funny joke. Blah, blah, blah.
Yeah.
All right.
Yeah,
Well,
cool. All right, man.
that's all I got, buddy.
Yeah, no, it's that was an early one, and got a few things to think about. Okay.
All right. I'll stop recording.